Good morning all, Charlie here. Just sort of follow-on video from the last one just to cover off on a few bits and pieces. Firstly, a big thank you to those who participated in that sort of straw poll. The results were quite telling. Suffice to say, no desire for doing a bass rig, which is fine by me, no problems there. But certainly a desire to do a portable rig of some sort. Pretty well split between the CW and the SSB. I've decided I will go with the CW for a start, because I really do need to get back into Morse and getting the old proficiency back up again. It's been quite some time. As an aside, when I first got my ticket many years ago, the person who taught me Morse said you'd be well placed to, when you get your ticket, to unplug your microphone from the radio and just use Morse for the first 6 months to a year, which I actually did, and I thought it was very useful. But yeah, that's sort of fallen by the wayside, and I've only sort of really got back into amateur radio in the last year or so. So I'm going to start by doing the CW rig, and then I'll move on to the SSB rig. What I am going to do, I'm going to constrain myself with regards to the CW to endeavour to make it fit into this box here. Doesn't give me a huge amount of room, and when it comes to the available real estate, so that's the piece of copper that will fit in there, and that'll be the small dividing wall that will divide the receiver from the transmit circuitry. So by the time you sort of add in your microcontroller, the SI5351, there'll be a filter up there. There's not going to be a huge amount of room, but that's the constraint, so that should make it a bit of a challenge. And then when we come after that to the portable SSB rig, we'll be a little bit more generous and we'll build that into this one here. So still the same footprint, but just sort of slightly higher, which has the ability then to use a slightly higher dividing wall, which then you can mount maybe some low pass or band pass filter on that, which just makes life just a little bit easier. So anyway, so in terms of the CW rig, my thinking is to make it a single conversion based around two ADE-1 mixers. And so just to very briefly run through it, RF comes in, it'll go through a bandpass filter, so it's 40 megahertz, so we'll go to, say again, 40 meters, so it'll be through a 7 meg bandpass filter, simple RF amplifier, then into the mixer, and then an IF amplifier. I think all three IF amplifiers will just be simple 2N3904 Class A amplifiers at this stage, not bidirectional, and we'll talk about that in a sec. The filters we've talked about, and then a commercial 700 Hz, I think it is, CW filter for the frequency selective portion there, and the output of the last mixer into an AF amp. Probably using headphones for a start, with the option of plugging in a small speaker probably. Now on the transmit side of the house, what I'm thinking about doing is the SI5351 has three outputs. Traditionally, you've been using clock 0 and clock 2 to be the VFO and BFO respectively. And what I'm thinking for this rig is to use that third output and then synthesize the desired frequency directly. So in this case, 7 megahertz. That's a square wave. So clean it up with a low pass filter, produce a nice sine wave, and then switch it. It's low level coming out of here, so I think switching that directly shouldn't be a problem, so that's what I'm currently thinking. And then the output of that key through a Class A drive amplifier and then into a Class C power amplifier to get out. Now at this stage I'm using, oopsie daisy, this power brick for the power source. So I've got a few restrictions there. So in this particular case I've got 12 volts, 6000 milliampere hour, with a maximum discharge current of 3 amps. So that's going to be my limitation. Whatever I do for the power amplifier, I need to restrain it to be no more than 3 amps on transmit. So that's the current thinking for that particular amplifier. Now for the display, in the past I've been using OLEDs, and while they've been really nice and crisp and really easy to read, they have been quite noisy in terms of RF. So I think for this one what I'll try and do, and I've got them on order, is a cheap single unit 4 segments of the old 8 segment LEDs. That's what I'm thinking about using. It's got a 4-wire input, so VCC and ground and the data and clock, which will make it nice and easy to drive and not requiring so many pins that you traditionally have with those. But I've only got 4 digits to play with. So my current thinking is, if we were to pick on, say, 7023.4 kilohertz, I don't need to display the 7 because this is only going to be a 40 meter radio, so it's always going to be preceded by a 7. So I'm only going to display those digits there. So the hundreds, tens and ones of kilohertz, and then the hundreds of the hertz in the 4 segments. I don't think I need to tune any lower than that. I think being able to tune the hundreds of hertz would be sufficient resolution to get the right pitch and to get on frequency. Something I didn't mention about frequency puts me back on to side tone. So what I'm thinking about the side tone for this radio is to use the receive chain. So at the moment, if I'm tuned to say 7 megahertz, I want to transmit on 7 megahertz. I know there's going to be a small amount of leakage or RF getting across what will be that now open TR switch, and there'll be enough RF there to be detected with an output. But if I'm transmitting on 7 and tuned to 7, then I'll essentially have a 0 beat, which will give me nothing on the output. So what I'm thinking about doing, I'll tell the microprocessor, so it'll sense the PTT line, and whenever it's keyed, I'm going to tell the microprocessor off tune the receive VFO by, pick a number, 700 Hz. So therefore I'll get that 700 Hz beat going all the way through, which will serve as my side tone. As soon as it goes back to receive, that offset on the VFO is removed, and we're back on frequency for receive. So that's what I'm thinking in terms of the side tone, and I don't see why that shouldn't work. But hey, it's all about experimenting, and that's the current thinking. Anyway, so I'll draw a line under that. That's going to be the next build with the constraints, and we'll see how that plays out. There's something else I want to touch on, was a comment I made about maths in the comment section, and a bit of a self-imposed restriction. I'll show that. Self-imposed restriction that I don't just want to straight up copy circuits off the internet or out of a book. That I'd really like to try and at least understand how they work before using them. And a good point in case here is a circuit which appears in the EMRFD book, designed by Plessy for the Manpack transceiver series. It's a bidirectional amplifier, which is quite elegant. Depending on bring that back a bit. Depending on these two switches here, which switch 6 volts or ground to these 200 ohm resistors, depends if which particular resistor, say again, transistor is turned on. So in the case of the NPN, when that's turned on, we have a signal flow in that direction, and when the PNP is turned on, we have signal flow in the other direction. So we get out of the one circuit this sort of bi-directional characteristics. In this particular case, this radio, say again, this amplifier was designed for 3.5 milliamps of biasing current and for 50 ohms. Now it was the 50 ohms bit which I was trying to work out, how do they work that out? It's been a long time since I've been in school, and I couldn't quite remember. So I sort of cast my mind back to, where is the non-feedback? Excuse me, I've got a circuit around here for the no feedback. Here we are. This is the one I wanted to bring up next. So I was thinking, sort of cast my mind back to simple amplifiers. So simple common emitter amplifier here, bypassed emitter resistor. It's pretty straightforward to work out what the impedance is looking in, or resistance looking in, if we ignore any capacitance and inductance. In this particular case it's beta RE, where RE is made up of the little re, which is the input resistance to the actual BJT itself, plus any bypassed portion of the external emitter resistor. So little re, as we know, is 26 divided by IE in milliamps. And I just say RE is the bypass portion. So for example, if we were to introduce a little bit of emitter degeneration, just to knock down our overall gain, then that RE portion there would be that one there. This one would be ignored because it's bypassed. And the other thing to think about too, in terms of beta RE, that's beta AC. So the beta AC would be our gain, current gain bandwidth product. So for a 2N3904, that's quoted at 300 megahertz divided by our frequency of operation. So just a bit, so bear that one in mind. So suffice to say, for a no feedback amplifier, it's a pretty straightforward process to work out what, at least in this particular case, looking in would actually be. However, when you start to introduce, like in this particular case, some feedback through that 1k ohm resistor, it becomes a little bit more complex, and you can't just do that simple maths to work out the 50 ohms. And even then, it's not necessarily 50 ohms looking in, it's all about maximum power transfer. So when our input impedance matches our source impedance, then we get the maximum power being transferred. In this particular case, this was designed for a 50 ohm match. So which one I want to talk about first? I'll talk about this one. Yeah. So you can, through some clever manipulation with our feedback resistor here, RF, and our emitter resistor, you can essentially design that to have any input and output impedance you want. In this particular case, what you need to do, and what they get into in the textbooks, which I had to dig out just to get my brain sort of back into it again, was some nodal analysis. And I certainly don't want to delve into this, but suffice to say, the bit here in the circle is the actual transistor itself, and we have our external feedback resistor, that one there. We have the load, notionally shown here at earth because the VCC rail is decoupled to earth. We have our emitter resistor down here. We have our source resistance from whatever source is coming in. And then we start to work out what the currents are doing. So I use electron flow, so current comes up and it gets divided. It goes through here, gets recombined. There's a portion going through here, up through any biasing resistors. And you essentially work out some equations to define what those currents are. You can then, through Ohm's law, substitute in, for example, IB. Rather than saying IB, you can substitute in, well, IB actually equals the voltage at the base minus the voltage at the emitter divided by little re, and you'll get that current going through here. So it's just straight out Ohm's law. So by doing that, so by rewriting these three current equations in terms of voltages and resistances, you come up with three equations with three unknowns: VB, VE and VC. And then, and like I say, I don't want to delve into this too much, but you can then rewrite, for example, the first equation in terms of one of those unknowns. So let's just pick on VB. So it'll be something like VB equals blah blah blah, and then you can substitute in blah 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 into the second equation wherever you see VB. You can then conversely do exactly the same thing. Now rewrite that second one in terms of the third unknown, substitute it into the third equation, and then you can solve for the first unknown. Feed that back into the second equation, you can now solve for the second unknown, feed both those back into the first equation, and you can solve for the third unknown. And then that allows you to, once you've got those three equations and those three unknowns solved, essentially put it into a computer, and you can start throwing in different values of RS and RLs, how much voltage you got going in, and suddenly you can start to work out, or how much gain have I got, how much current's now going through the load, what's the power, and then you can start to basically design this to be whatever you want. That was a terribly oversimplified explanation, no doubt full of holes, but I guess what I was trying to say is it's just not a simple process of doing a couple of lines of maths and you've worked it out. There's quite a bit of iteration involved, and you'll see in some of the textbooks tables of RF and tables of RE to give you specific input and output impedances, which is really quite interesting. There are a couple of rules of thumb though that are used. So in terms of that's one there. So our RF, going back from the collector back to the base, times R little e, where R little e equals little re, which we mentioned before. That's the resistance in the actual device itself, plus Re, which is our bypass, or our degeneration here, our feedback here. And if you use that relationship, equals, so those two multiplied together equals our source times our load resistance, you then can, for example a set Re of say 10 ohms, you can then solve for what RF should be, and we'll just make that up to a standard value of say 820. So this is an approach I think I might start playing around with in some of the amplifiers for the multi-band rigs, where there's a need to try and flatten the gain across a much wider bandwidth. But for the next particular build, because it's just going to be set on 40 megahertz for our CW rig, I'm not going to worry too much about that. We'll just probably just go straight into, for those three amplifiers up here and this one down here, just probably a common emitter, voltage divider biasing, and then through LT Spice look to fine-tune those for maximum gain, or as much gain as I can get on that 40 meter band. So that'll be the process there. But I just want to sort of clarify that statement about the maths, and I'm not going to, and I certainly don't intend to be able to write every circuit down line by line, but at least it'd be nice to try and understand a little bit more about what's going on. Right, I have rambled on way too long, so I will leave that there. Again, thanks to those who put in some information and some votes. That's much appreciated, and hopefully I've got a few components turning up in the mail, and we can start melting some solder and see if we can't put this together and hopefully squeeze it into this little box, which should be quite good. Anyway, 73's all. Thanks very much, and we'll see you shortly.